Alright, so today we're going to be determining convergence or divergence of the series starting at 1 going to infinity of e to the power of 1 over n plus 2 parentheses minus e to the power of 1 over n. Now what does this mean? This is asking us, as we have different values for n being plugged into the exponent of e, what will we get when we add those, right? We're going to have that value added to the value as we have 2 for n. So let me just write that down really quick, right? We have the s of 1, the sum for 1, well, for n equals 1. That becomes e to the power of 1 over 1 plus 2, because we're plugging in 1 for n, minus e to the power of 1 over 1, because, yeah, 1 over n. Now if we have s of 2, we have e to the power of 1 over 1 plus 2. We're going to add the first one to the second one when we plug in 2 for n. So we just copy that, e to the power of 1 over 1. We're going to add, plugging in 2 now, for n. E to the power of 1 over 2 plus 2 minus e to the power of 1 over 2. Now, we got to do this and continue this. This is s of 1, this is s of 2. You don't have to write this down. It helps me remember, at least especially starting out. What we got to do now is continue this pattern and plugging in whatever number we have and the ones before it and adding those all together until we reach infinity. I don't know about you, but I don't have an infinite amount of time, at least not until Saturday. So what we could do is we could just skip ahead to, I don't know, s of, let's do 10, right? So this is going to take a little while. We're just going to copy it down. E to the power of 1 over 1 plus 2 minus e to the power of 1 plus e to the power of 1 over 4 plus 2 plus 2, right? E to the power of 1 over 2, right? We're going to keep going until we reach 10. Okay, plus e to the power of 1 over, when n, now this is for n equals 3, so 3 plus 2 is 5, minus e to the power of 1 over 3. Plus e to the power of 1 over, so now for n equals 4, for the fourth term, 4 plus 2 is 6, minus e to the power of 1 over 4. Now I'm hoping you'll notice that there's a pattern here. We don't have to do the arithmetic for every individual exponent of e, because if you'll notice, 1 plus 2, right, 1 plus 2, believe it or not, is actually 3. And then we have 1 over 3, 1 over 4, 1 over 5, 1 over 6. Similarly, this is 1 over 1, right, as we stated before, 1 over 1, 1 over 2, 1 over 3, 1 over 4. Now, I don't know if you're able to pick that up right away, but we could just continue that pattern. E to the power of 1 over 7 minus e to the power of 1 over 5. And if you don't trust me, you can always check your work. This is the first term, second term, third term, fourth term. This is when n equals 5, right? N equals 5. 5 plus 2 is 7. 1 over 7, 1 over 7. We're plugging in 5, 1 over n, the fifth term, 1 over 5, right? So you could just keep, if you need to, check your work. I encourage it. We're just going to keep up that pattern. E to the power of 1 over 8 minus e to the power of 1 over 6 plus e to the power of 1 over 9 plus e to the power of 1 over 7 plus e to the power of 1 over 10 minus e to the power of 1 over 8 minus, plus e to the power of 1 over 11 minus e to the power of 1 over 9 plus e to the power of 1 over 12 minus e to the power of 1 over 10. This is the 10th term when n is 10. So therefore, this whole thing right here is the s of 10 for our series. So what can we do with this information? What we could do is we can notice that these are all like terms and they're all operations of addition and subtraction. There's no multiplication, there's no division at all whatsoever. So what we could do is notice that we have a positive e to the 1/3 and a negative e to the 1/3, which means we could cancel that out. And we can keep doing that for every single term that matches. So we have that one, we have, I don't know, over here, 1 over 5, positive 1 over 5, we have e to the 1/7, negative e to the 1/7, e to the negative 1/8, e to the positive 1/8, and e to the 1/6, negative e to the 1/6, and so forth and so forth. And the last one would be this one right here, positive, negative, and positive, negative, which leaves us with negative e minus e to the 1/2 plus, this is left over, e to the 1/11 plus e to the 1/12. E to the 1/12, right? Because those are what are left over after we cancel everything out. Okay. So, like, okay, we get it. Well, so what? What we can infer is that as you take different sums of the series, you're going to notice that they're all going to have a negative e and a negative e to the 1/2, right? The sum of one, the summation for n equals 1, that's what we start with. We have e to the 1/3, or my bad, we have e to the 1/3 minus e, right? For the summation of 2, we have e to the 1/1 plus 2, and then so forth and so forth. But as we go further down the line, we're going to notice that every single summation includes a negative e and a negative e to the 1/2. So maybe not so much these probably won't have it, but as you go farther down the line, as you approach infinity, right, that's what they're asking, as it approaches infinity, you're always going to have, you could check if you like, we're always going to have a negative e and a negative e to the 1/2 left over. But for the summation of 10, we'll notice that we have e to the 1/11 and e to the 1/12, meaning 1 is 1 more than 10, and 12 is 2 more than 10. So we can infer that it is basically negative e minus e to the 1/2 plus e to the 1/n plus 1 plus e to the 1/n plus 2. So now that we have something that we can work with here, we can determine whether or not it is convergent or divergent by taking the limit, because now this becomes s of n rather than s of 1, 2, 3, so forth and so forth. We have a general formula to determine the series of terms or fucking whatever. So what we could do now is, because we have something more concrete than this, because to determine whether or not this is convergent or divergent, we got to take the limit, right? And we take the limit as n approaches infinity of e to the 1/n plus 2. This becomes 1/infinity, which means e to the 0, right? 1/infinity is 0, e to the 0 is 1. And then e to the 1/n, you take the limit of that as n approaches infinity, that's also e to the 0, which is also 1. So when you take the limit of this entire formula right here, you end up with 0. And using the divergence test, when you take the limit of that series or of the set of terms, it can't be 0 if you want it to work, and therefore the divergence test fails. And just because the divergence test fails, that does not automatically mean it is convergent. That is an assumption you cannot make. So now that we have something else, we can take the limit of that. So let's do that. The limit as n approaches infinity of s of n equals negative e minus e to the 1/2. Now we got something else we could work with here. Like we said before, e to the power of 1/n as n approaches infinity, that is 1/infinity, which is 0. So e to the 0 power is 1. Similarly, e to the 1/n plus 2, that is the same thing as 1/infinity. So that is also e to the 0, which is 1. Okay. 1 plus 1 is 2, and then negative e minus e to the 1/2 is 2 minus e minus the square root of e. Because e to the 1/2 is the same thing as the square root of e. So because the limit as n approaches infinity of our series, because it's the limit of our summations, we could infer that it is not infinity. So therefore, by the telescoping series, well, obviously in the very beginning, we have to establish that let a of n equal e to the 1 over n plus 2, and then minus e to the 1 over n. That's kind of sloppy of me, I'm sorry. But we have to establish that that is a of n, and therefore we could go down here and say the series, by the telescoping series, a of n is in fact convergent. Meaning that if you add up all these terms, if you add up everything as s approaches infinity, you will always end up with a convergent value. It will not go to infinity. It will not always change. It will converge to one value. Q, E, D. Thank you.